dispersion. If somebody was asked to, like I asked the class, when we learned about it the first time, if you had to use your common sense to talk about a typical separation or dispersion or variation among these numbers, most people said, well, the number should be around 2. These numbers seem to be about 2 apart, and 2 should quantify the amount of dispersion. The answer should be 2. The question is, what kind of formula gives us an answer close to 2? Well, the formula, so first of all, you've got to calculate the middle number, which in this case we said is 4. And how far is 2 compared to 4? Is 2 below the average? 4 is exactly on top of the average. 6 is 2 above the average. So we have 3 measurements of how close everything is to the middle. And by taking an average of these 3, we're going to get a sense of what is the typical separation among the numbers. The problem is when you take an average of a negative and a positive, they cancel out. And if the sum is going to turn out to be, the sum turns out to be 0, which is not the answer we'd hope to get. If I asked you, what is the dispersion among these numbers, you would say 0, you'd be right. But here, the number is not, the dispersion is not 0, and we're getting an answer of 0. So the formula says, take each number and see how far it is from the average, and then add up all those numbers and get an average of those deviations, called the average, by dividing by the sample size. This formula is not working out for us. It's giving us an answer of 0 divided by 3, which is 0, but the common sense answer should be close to 2. So as an improvement, somebody suggested in class that we take this minus number and get rid of the minus sign by squaring it. We're taking the absolute value of the minus and squaring is better. And you get minus 2 squared becomes positive 4. 0 squared stays as 0. 2 squared is positive still. And then you take the average of the squares. So the formula, if you modify it with that new approach, would have a little square in it to get rid of the minus sign. And basically you're focusing on the third column. The sum here is 8. And the formula says take the sum of all those squares, which is in this case 8, and get an average by dividing by how many numbers you have, and you're going to get, comes out to 2.87. Now 2.87 we can live with because, 2.67, because the common sense answer of 2 may be off, maybe my common sense is off by a little bit. So maybe the mathematical answer is better for some reason, which I can't explain. But it turns out that this formula, while it's basically correct, has to be improved by 2 further steps to make it the answer exactly 2. And we talked about the next improvement is instead of dividing by the number of numbers, because you want to get an average. So we're adding them up dividing by 3. But technically speaking, we're measuring the separations among the numbers. And if you have 3 numbers, you only have 2 separations. And if you have 5 numbers, you have 4 separations. So it makes sense in a certain, and it can be proven mathematically, to not divide by the number of numbers you started with, but 1 less. So if you do that, it makes the answer further from our final answer. It comes out to 4. But it turns out what I just proved for you, calculated for you by this process, of listing the numbers, subtracting out the average, squaring it, adding it, and dividing by n minus 1, like 5 steps, that answer is the right answer to the question. So on the test, I would ask you, calculate the variance of these 3 numbers. By going through these steps, the final answer for it is correct. But it turns out there's another formula based on that called the standard deviation. And the standard deviation, which is symbolized of the sample, there's also a standard deviation of the population, which we're not talking about, it's not that common, which is symbolized by the S without the square. Remember, this has an S with a square here. This has the S without the square, is literally the square root of this answer. Or if you want to write it down as an actual formula, the square root of the original formula. Which, if you want to do it in terms of numbers, is the square root of 4, which is equal to 2. Why are we taking a square root? Because this process of getting rid of the minus sign artificially inflated the numbers. So at the end of the problem, you have to reverse that. Taking a square root, it reverses the squaring. And by doing that, we end up with an answer which really can be made commonsensically explained that the separation among these numbers is 2. And that, of course, is what we hope to get. So that's the demonstration. Okay, where is, so I'm sorry. And then, what's your name? Is the CV called the coefficient of variation. And basically calculates the standard deviation, but comparing it to the average and dividing by some number is a good way of comparing it. And in our example, at least, the standard deviation we just said was 2. That's from this calculation over here. The x bar we said was 4. So it's 2 divided by 4. But you expressed it as a percentage. So 2 out of 4 is a half, but a half is 50%. So you multiply it by 100%. So this comes out to 50%. So I'm not going to spend the time right now to explain it. But basically, you're calculating the standard deviation, not in a vacuum, but in the context of the average. And the very last formula, which I'll take an answer in you have a question about this?
Yeah.
Yes?
What does that number tell you?
Okay. it tells you, for example, let's say you're measuring, I think, to do quickly the example I gave in class, I believe. Maybe we didn't do it in class, I'm not sure. We measure a bunch of baby cats, 1 ounce, 2 ounce, 3 ounces. And a bunch of baby elephants, 400 pounds, 500 pounds, 600 pounds. So the question is, which species has babies that are more further away or closer to each other? Are there siblings? So, well, this looks like they're 100 pounds apart, and here they're only 1 ounce apart. So you would say cats are very close to each other, and elephants are very far from each other. But that's not really the whole story, because cats, so we can say the standard deviation is 1 for the cats, and the standard deviation is 100 pounds for the elephant. But 100 pounds for an elephant is like nothing. But 1 ounce for a cat is half its body weight. So we can say 50% of his body weight is sort of related to the standard deviation. But 100 divided by the x bar, or 500, only 20%. So from that point of view, you could say the baby elephants are closer together. That's how it's a little used. This also uses laboratory work a lot. The last formula, I think, of this series in chapter 3 is something which I know appears in the online stuff. That's called a z-score. By looking at a z-score of 1, it means I scored 1 standard deviation above the average. That's how you interpret it. And of course, somebody had a 2. 2 take away 4 is -2. It'll be a z-score of -1. It means 1 standard deviation below the average. And I'm going to spend more time discussing this. What we need right now is just a calculator, which is a pretty simple formula to calculate.